organizers for inviting me and for giving me the opportunity to speak in this beautiful location. I'm going to use this opportunity to speak about a joint project with my co-authors, who are Volker Betz from Darmstadt, who's a mathematical physicist, Steffen Dereich from Münster, and Cécile Mayer from Bath, who are both probabilists. So what I'm going to present to you is a pretty high-level view of the phenomenon of condensation, and I hope to discover by studying this from this high-level view the emergence of condensation, some general principles that might be of wider interest. So what I mean by condensation, very loosely speaking, we have a complex system and we say that it undergoes condensation if a positive fraction of a continuously distributed quantity gets concentrated in a single state asymptotically as time goes to infinity. So the aim of the project is to understand the dynamics of this condensation, so how the condensate can build up or emerge in such a system. So this quantity that occurs here could be the distribution of energy, or it could be the distribution of fitness in some biological model. So the plan for the talk is as follows. I will spend a considerable amount of time on the simplest possible model. This is called Kingman's model of selection and mutation. So this is a model so simple that we can actually understand what's going on, and so sort of this is the guiding model for what follows. In the second part, I briefly show how what we've learned from this simple model can be generalized to cover maybe somewhat more interesting objects, PDEs with condensation, by sort of generalizing the principles of the simple model. And in the third part, I'm going to speak about the model that actually interests me, which is a stochastic model. So the models in 1 and 2 are actually deterministic. So in the stochastic model, a particle model called the reinforced branching process, I don't understand how the condensate emerges, and I'm looking at a slightly different question in order to improve the understanding there. So let us start with the simple model, Kingman's model of selection and mutation. So this model, introduced by John Kingman in 1974, as a model for the balance of selection and mutation in a population, consists, a mathematical model, of a sequence of probability measures n, say on the unit interval 0, 1, and this unit interval here represents fitnesses. So n, distribution of fitnesses, 1 being very fit particles, particles with a small number being unfit. And this describes the distribution of fitnesses in the nth generation. So there are 2 model parameters, a probability measure mu on the interval 0, 1, the so-called, which plays the role of the mutant fitness distribution, and a number beta between 0 and 1, which is the mutation probability. And the model goes like this. You start with some distribution of fitness. Actually, it could be the mutant fitness distribution mu, and it evolves in the following way. If Pn is the fitness distribution in the nth generation, we get the fitness distribution in the next generation by in the following way. So a proportion beta of the population undergoes mutation, and after the mutation, its fitness distribution is given by the mutant fitness distribution mu, and the proportion 1 minus beta of the population gets selected, and the fitness is sort of the selective parameter. So we select proportionally to the fitness x from the population in the nth generation, and of course this gets normalized by Wn, which is the integral over x Pn dx. So a proportion 1 minus beta of the genes in the new generation are resampled from the existing population using fitness as a selective criterion, and the rest have undergone mutation. It's a kind of house of cards model. If you have a mutation, then all the genetic information is lost, and you get a new fitness according to mu, which is completely independent of your previous fitness. Let me just copy this equation here for later reference. So distribution in the n plus first generation, you get 1 minus beta times what you select from the previous generation and the proportion beta from the mutant fitness distribution, and the Wn is the normalizing factor integral from 0 to 1 x Pn dx. Okay, so what can happen here? Well, if you look at the population after n generations, there are individuals that come from a recent mutation that sort of survive a couple of selection steps, and the fitness distribution from these will be somehow similar to the mutant fitness distribution mu. But if the mutant fitness, if this term is not likely able to produce many fit particles, it could also be that some particles initially in the system, a small number of particles initially in the system with a high fitness, a fitness near to 1, be selected consistently over a long time, and then they can form a part of the population with high fitnesses. And this is indeed what happens. It's not very hard to show. There is a condensation transition in the system. So if this term here, which sort of measures the ability of the mutations to create fit particles, so this is large, if either the mutation probability is large or this mu has a lot of mass near 1, so that this integrand is high. So if this mutation ability of the mutation to produce fit particles is big, then our distribution Pn converges to a limiting distribution of this form. So that's just a tilted version of the fitness distribution. It's absolutely continuous with respect to mu, so there is no condensation here. But if this condition fails, so if this integral is less than 1, then there's a convergence of this fitness distribution to a distribution which has parts. This bulk part, where the fitness is proportional to our mutant fitness distribution mu, and then there's a Dirac in 1, that's the fittest possible state, with the mass gamma of beta, which is this slack 1 minus this term here, which in the condensation case is less than 1. So this is this. We say that in this case that condensation occurs and the condensate has psi gamma of beta. So these formulas you easily get if you drop this n here and solve the equation with respect to p. Okay, so this is what Kingman observed. What we're interested in is how this condensate, which in the limit shows itself as this Dirac part here, how this is built up over time. And there is the following theorem that's sort of at the beginning of our investigation, and that tells us how this happens. So again, we start with P0 being the fitness distribution. This is not so important. We assume that this condition 1, maybe I should write it down as well, fails. So condition 1 is the condition of condensation. Okay, so if this fails, so with condensation, and if the mutant fitness distribution has the scaling that if if you look at the mass within distance x of the maximal fitness value, if this is regular, varying at 0, so behaves x to the alpha for some index alpha, then if you look at the mass in the interval 1 minus x over n1, this converges to this function, and this means condensate at a large finite time n. It's the shape of a gamma distribution. Here you recognize the density of a gamma distribution with shape parameter alpha. So what the picture says here is, so on this axis here is the fitness, and this is the distribution, this is the distribution of the fitnesses at a large time. There is bulk part, which is proportional to the mu I've chosen, and then there is this part here that will, in the limit, become this Dirac n1, and the theorem says that for finite time, the shape looks like such a gamma distribution here, as can be seen in this picture. So, the lesson, so what we've learned from this is that in this condensation case, there's the bulk and there's the condensate, and the shape of the bulk depends on our mutant fitness distribution mu, on our parameter, but the shape of this condensate here is universal. So independent of the exact form of mu, this looks like the gamma distribution. And this sort of makes us suspicious that this might be a more general principle, that if you have this type of condensation, that the shape of the distribution of this condensate might typically have this gamma, might be of this gamma shape there. So this is what we want to investigate. But before I look at other models, I take a close look and show you what's behind this theorem here. So what's the idea? Well, if you look at this equation, this is of course a nonlinear equation, because the Pn occurs not only here, but also enters into this Wn here. But if you pretend to know these Wn's, these mean fitnesses here in the nth generation, if you pretend to know this sequence, then of course it's a linear equation, and then you can successively plug this in, and you get a formula for Pn dx in terms of these little Wn. These are these mean fitnesses here, which I've multiplied up to become this capital Wn. So this formula can also be easily interpreted if you look at the distribution of the fitnesses in the nth generation. This R is, every individual in the nth generation comes from a mutation, and this mutation is R generations back. Equals 0 is the last thing was a mutation, and if you have a finite R, then you have R times a selection. So for example, this is where this x to the R comes from, and also the factors W that remain there. There was also the 1 minus beta to the R. There are R selection steps and one mutation step before it. So the interpretation here is that this sort of decomposes the population in the nth generation according to how many steps back you have to go in order to see the last mutation that led to the fitness of the particle. Okay. So if you look at this, let's look at this even more. If you look at this and yourself from where does, so this is always a probability measure. This is conserved. The total mass is conserved. And so where does the mass come from? So remember that mu is on the interval 0, 1, so this x is less than 1. So if r is large, then the x to the power r is potentially small. But if r is very small, so that's recent mutations, then there will be then this is all of order 1, and there will be a contribution coming from this recent mutations. So there's certainly going to be a contribution from very small values of R, and it's going to look like beta times geometric series, and that's the term that you actually see in the limit. But there's also a chance that maybe there's a contribution coming from from large values of R, when R is n or n minus something finite, because although in this case the x, let's look at R equals n, x to the n is potentially small, x could be very close to 1, and there is this term which is 1 over wn. The w's, the mean fitnesses, are numbers less than 1, and therefore the wn is a small number, and 1 over wn is a big number that could potentially compensate the smallness of x to the n here. And in order to see whether this is the case, we have to study this wn together with this 1 minus beta terms. And if you look at this, if you define un to be wn times 1 minus beta to the 1 minus n, and you integrate this equation here in x, you get a renewal equation where this mass mu r at the nth moment with respect to mu, and these renewal equations are well understood, and in our condensation case, these un decay like a constant multiple of n to the minus alpha. So in particular, they go to 0 and are able to compensate this x to the r. So in the condensation case, contributions to this p and dx come from small values of r, the bulk, always, but in the condensation case also from small values of n minus r. So that's the condensate case. And if you look at the shape of the condensate, so this is the x dependence here for values of r that are near n, you see it's just the only x dependence is this x to the n. So the sort of the shape comes from these x to the n, measures x to the n mu dx. So the asymptotic shape of p and dx near x approximately 1 agrees with that of this mu n dx. And if you check the mu n in a neighborhood of 1 with a width 1 over n, you can write this as an integral here, the Stieltjes integral from 0 to xn, if you just change the measure, and if you substitute z as y to the n here, you see here a term converges to the exponential, e to the minus y. This term here, by the regular assumption of regular variation, goes like y to the alpha times the term mu of 1 minus 1 over n1, which you can take out, and the dy to the alpha becomes alpha times y to the alpha minus 1, and then you see exactly the gamma term coming up here, independently of the exact shape of the mu. Okay, so that's in essence the proof. So again, our remark was the shape of the bulk is a modification of mu. The shape of the condensate seems to be universal. So in this model, it's not depending on the finer details of mu, but for this to be really a universal phenomenon, we would like to see this happening in more complex, in a wider range of models, and in particular in stochastic models. Yes? So the alpha comes from the fact that I'm assuming that mu is regularly varying, so that this mu of, essentially mu of 1 minus x1 behaves like x to the alpha. Okay, mu of this interval. Okay, so it's a bit more, it's a bit more general. I'm just assuming that mu of 1 minus x, I'm just assuming that this behaves like y to the alpha times this term with y equals 1, which is regularly varying. So logarithmic terms I could still absorb. Indeed, this index alpha comes out of the mu. You could, but there are not many possibilities for this. If you can have this polynomial behavior, and if you have quicker thing, then you could prove something Gaussian there. But this doesn't happen in the interesting examples, so I'm not going to speak about this. Yes, so there is some feature of the mu that enters in the parameter, but the gamma distribution is universal there. Okay. Okay. So it's not for this biological model. It's more natural to say large values are of higher fitnesses. I'm going to. Okay. So what I'm going to do in the next slide is I'm going to show you how to sort of, or I'm going to tell you what comes out if you take this idea, if you generalize it, and what we've done because we want to cover more examples, we move the condensate 1 to 0. So that comes now. So we're now looking at sort of what we can get out of this idea by extending it by using more mathematics. So we now look at partial differential equations. So instead of, we make the time continuous because that's how most models are written, and we get a PDE of the form that the time derivative of ptx, I've moved away from, I now describe this as a density, not a measure. This is some function b of the pt, depending on x, times ptx, plus some function c of pt. There's an x to the alpha that I take out. And our theorem says the following. So we assume we start this PDE. We look at the solution with the initial condition, which is essentially x to the alpha naught for some positive alpha naught, and some continuous eta, which is positive 0. And we assume that the ptx dx converges in a suitable sense to a stationary limit which shows the condensation. So the limit of this measure ptx dx is measure p infinity dx, which has q of x dx, this bulk part, and rho times the Dirac in 0. Now I've moved the condensate 0 because this is more natural in general. So if you have in a certain sense convergence to this stationary limit, so this sense of convergence includes convergence of these terms b of pt to b of p infinity and c of pt to c of p infinity, and the limit should be stationary in the sense that when I plug in the b of p infinity and the p infinity and c of p infinity here, the right-hand side should be 0. If this taking out of this x to the alpha leads to a positive value here at 0, which I call C1, and the q of x is scaled like x to the alpha minus 1, then I get that the density at x over t multiplied with 1 over t, because we're no longer we're now in the density case, so that's together with x, it would be the measure here. And this converges to the density of a gamma distribution with parameter beta, which is normally alpha, unless we've chosen unless we've chosen a smaller alpha naught. Yes, because the x is now small. A smaller alpha naught, in which case the initial condition dominates the behavior. And a scale parameter, which is the product of these two constants. So this is the if you sort of take the simple ideas of our model here and sort of extend them to this PDE setup, then you can get that for a differential equation that converges in a suitable sense, or that shows condensation in a suitable sense, the shape of the condensate here is also always of this form. Of course, the crucial question is, are there examples? And we've scanned literature, and indeed we found some examples for energy distributions in the context of phenomenological models for Bose-Einstein condensation. So I don't understand exactly how they're derived, but if you look at the literature, you see, for example, this model of Escobedo, Michler, and Velasquez, this kind of equation. You can write it exactly in the form that this is some function of pt times ptx plus x squared times function c of pt, and it satisfies our conditions. So in this case, you can see that the buildup of the condensate follows a gamma distribution. And there's a similar model earlier, so this is maybe 10 years old. This is from the late 80s of Buffet, de Smet, and Poulet, who also look at the energy distribution of a Bose gas, and to write down such an equation here, where again we can see that it satisfies our framework. We can see that we have a gamma distribution, this time with the index given by this power half, which comes from the density of states for a Bose gas in a three-dimensional box. That can be studied, but they're deterministic, and what I'm actually interested in is stochastic models. So yes? Yes, so in these models, this is a good question. In these models, the condensation happens at time t equals infinity. So there are other models, maybe more elaborate models, like the Boltzmann-Nordheim model and so on, where this can happen at finite time, and we can't treat them with our method. So that's too irregular for our purpose. But it would be interesting to understand this, but we've not been able to deal with that, although it was our initial goal. Okay. Right. So what I'm going to explain in the third part is now a stochastic model, somewhat similar to the Kingman model, but has a typical difficulty of a stochastic model, and it shows condensation, but well, we'll see. Okay. So this is the reinforced branching process. So in the reinforced branching model, it's a stochastic version of Kingman's model in the sense that there are not a sort of continuous distribution of the fitnesses, but there are actual particles and fitnesses in the model. The parameters are the same. So there's a mutation probability beta and the mutant fitness distribution, which is a probability measure on the interval 0, 1. And the model is a branching process in continuous time. We start with an initial particle which has random fitness chosen according to the mutant fitness distribution mu. And particles with fitness, all the particles live forever, and particles with fitness f produce single offspring with rate f. So that means that if a particle, at any time the particle with fitness f has an exponential clock with mean 1 over f, and after when this exponential clock rings, it produces one offspring particle, and the offspring particle can either be of the same type, so it inherits the fitness of the parent, and this happens with probability 1 minus beta, or it's a mutant, it mutates with probability beta, in which case the fitness is drawn from our mutant fitness distribution mu. Okay, so at any time t, state of the system is a finite number of particles that have some fitness in 0, 1, and the interesting quantity for us is psi of t, which is the empirical fitness distribution. So psi t of A is the number of particles with fitness in A, alive at time t, divided by the total number of particles alive at time t. It's called reinforced because, so when you think that a particle is born then it selects its parent according to the fitness. So every existing particle has a chance proportional to its fitness of being the parent of the newborn particle. So that's in urn models when you when you put a new ball in the urn and it sort of gets the fitness or gets the color of the thing that you've drawn. This is called reinforcement. So this is the reinforced comes from the language of urn models, and it comes from the fact that if you're fit, you have a double advantage. On the one hand, you produce more, but at the same time, when you produce more, then what you've produced also is a contender to be parent, and therefore this is a reinforcement procedure, and that actually leads to the condensation in this model, and which looks exactly the same as this model. Again, we have this criterion here, which is the criterion for absence of condensation. So if this holds, there exists this lambda star and the xi of the x, which is now a random measure, but it converges to almost surely to the same limit as in the Kingman model. And if one fails, you also have the convergence, but now with this Dirac, which is now again in 1 because this is nicer for this model, and the mass of the condensate is the slack 1 minus this term here. So if you know a little bit about branching processes, if you want to study, you might think this is not so hard because it's a multi-type branching process, right? So what you do is you set up, if you have finitely many types, you set up the matrix, which gives you at entry ij the rate at which a particle of type I produces particles at type j. And for this matrix, you look at the principal eigenvalue, which gives you the growth of the system, and the principal eigenfunctions that give you, for example, martingales with which you can study everything. Here we have a continuum of possible types, and everything what I said about the finite case goes through if the top of the spectrum is actually an eigenvalue. And this happens exactly under this condition. This condition is the top of the spectrum is not an eigenvalue, and all the probabilistic methods for starting this process break down. So that's why this is beyond the case that there is condensation, can be studied by sort of approximating the system by one which satisfies this. If this fails, it's very difficult to study this model. In particular, for example, we have no asymptotic expression for the number of particles in the system at time t. So under this assumption here, this is just purely exponential with the rate given by this lambda star. But without this assumption, it's complicated. It's quite subtle. So maybe my picture is next. Oh yes. Okay. So this is the picture. We've simulated this, and on this axis is time. On this axis is the fitness. So every family. If a mutant is born, then all the particles that are offspring of this mutant with the same type, with the same fitness, are their family. So every family has a time at which it's born, the mutant father, and the fitness. So that is sort of corresponds to a point in there. Of course, it grows. And I've indicated the growth, the size of the family at my final time here, t equals 12 in this picture, by this circle, represented by the area of the circle. So you see what happens in this picture. There are early particles with relatively high fitness, like these ones here, that have time to grow large families and give these big circles. And then, of course, it's exponentially growing. So a lot of families are born relatively late. They might have a small fitness, they might have a big fitness. If they have a big fitness like this one, it doesn't help them very much because there's no time to grow a family, although they might be very productive. If you're born at this time, just before my sort of deadline here, it doesn't help you very much. Okay, now the interesting thing about this picture is that the previous easy result here tells you that the contributions from all these many points here, small circles that are here, and the contribution from these big circles here that will eventually be are of the same order. And this is amazing. If you want to create this by just putting a point process of circles on this, you have to work your socks off to adapt all the parameters in a very subtle way to get this critical thing that these contribution and these contribution are of the same order. So my colleague Stefan Derich has done this. It's a monster paper. But here it's for free. It's self-organizing. It's a case of this model has self-organized criticality. So it's self-organized so that the contribution of these big ones and the contribution of these many small ones are always on the same scale. So, and probably, models of self-organized criticality are very difficult. So this is one, and our conjecture is, maybe I should explain it with this picture again. So what's the conjecture? If I project on this fitness axis here, 0, 1, in such a way so every point gets just horizontally projected there, and the mass is proportional to the area of the circle, my claim is that this will look like, well, there's the bulk, and here these contributions make a gamma-shaped curve. Unfortunately, I can't prove that. It's my favorite problem. If you know any method how to prove this thing, I'll love you forever. But so far, I've not met anyone who could help me with this. So instead, what we're going to look at is as usual, I mean, we can't answer the question that we're actually interested in. We take a slightly different question that we can answer. And the different question is, how does the largest family behave? So the largest family in this picture is clearly the family corresponding to this circle. So there is a natural question. Can we say, when is it born? The largest family at this time, t, 12 here. When is it born? What's its fitness typically? And what's the size of this family? Okay. So again, we look at the mu here, regularly varying with index alpha. Here's my notation. So the empirical fitness distribution, this psi, is 1 over the number of particles, sum over all the families, Dirac in the fitness, and with the weight given by the size of the family. N of t is the number of particles, M of t is the number of families, Zn of t is the size of the nth born family at time t, and Fn is the fitness of the nth born family. And a question, so that's raised by Borks et al., and that reminds me, I've introduced this as a biological kind of model with mutation and selection, but it has different forms. And for example, if you know the Bianconi-Barabashi preferential attachment network, that's the same model, more or less. If you embed this in continuous time, this is the same model, and it can be studied with the same technology. So in this context, what is the birth time, fitness, and size of the largest family? Responds to the case of the question of the largest degree in this network model, which is sometimes called a model for Bose-Einstein condensation although I don't subscribe to that view very much. Okay, right. So the question is, what can we say about the largest family, the family that has the biggest number of members at time t? So this is not easy because we want this family can only grow if it's born early enough so that it has time to produce offspring. At the same time, at early times, there are not so many particles in the system, so we're not likely to see very high fitnesses. If we wait a little bit longer, it's exponentially growing, so there will be more fitnesses available. You will have fitter particles, but they will have less time to grow a family. So there is a optimization in there. And then the question is of whether the largest family is of the same order has the same order of size as the condensate. If this is the case, then it tells us something about the location of the condensate as well. Unfortunately, the answer to the second question is negative. Okay, right. So, so one feature here is that you start with one particle, and the size of the largest family, or the size of the total population, even at time t, depends on whether you're lucky and hit a fit particle very early, or whether you're unlucky and it takes a long time until you see fit particles. So there's some randomness in the system that will not go away. And this is reflected in this random variable t of t. So this is the first time where the number of families exceeds this deterministic quantity, and by this regular variation term, this is of the order log t times this constant alpha over lambda star. This is a standard result from extreme value statistic. And here is our theorem for the behavior of the largest family. So if you take S of t, the birth time of the largest family at time t, this behaves like this t of t plus some order 1 fixed real valued random variable in distribution. If you look at the fitness of the largest family, this goes to 1, and the difference, 1 minus this fitness, decays like a random variable v divided by t. And the v is gamma distributed, which is quite nice because we were looking for a gamma distribution, but it's not quite what we wanted. And if you look at the size of the largest family at time t, that behaves like e to the gamma, and then t minus this initial waiting time until you have enough particles. There, multiplied with a random constant that's exponential with some negative Frechet distributed, actually. Okay, so this is pretty complete information about the birth time, the fitness, and the size of the largest family. And if we now compare this, so this is the size of the family divided by the number of particles alive. So remember, the number of particles alive is also proportional to the size of the condensate. So the largest family divided by the size of the condensate, fortunately, goes to 0. So if you look at the distribution of the family sizes, the empirical distribution of family sizes, in T, so this has a part where the size with finite family sizes, then there is a kind of condensate that goes to infinity, but the largest value goes to infinity even faster. So in other words, the condensation, if it occurs, is non-extensive. There's no macroscopic contributions to condensation here. And this was very surprising because very careful simulations by Godrèche and Luc in 2010 don't show convergence to 0. In fact, from the simulations you would think that it probably converges to a constant. But this convergence is super slow. Sorry? Yes, very good. Okay. So on the other hand, it's a negative result. That's the largest families of smaller order than the condensate. Information about the condensate remains very difficult to get. Okay, so I just give you 2 minutes of why this is the case. So this picture is meant to be similar to the simulation picture with the circles. So when you analyze this largest family, you can sort of establish by a priori estimates that the largest family must be born in some box which is of width c and of height c over t attached to the maximum value. So families, the fittest and centered at this t of t. So the fittest families correspond to circles in this box here, and the mathematical work is then to zoom into this box. So you go over all the families to look at their birth time relative to the center of this box, their fitness scaled so that the distance to 1 is multiplied by t, and the size of the families scaled by e to the gamma t minus this t of t, and show that this 3-component point process converges to a Poisson point process with the given intensity, and that's well, it's quite a bit of work. But when you have this, then you can identify the largest family as the point with the largest 3rd component in this Poisson process. You can calculate all the distributions of the 1st, 2nd, and 3rd component of this point, and that's where you get the result from. And I think further details of how this is done, I spare you, and thank you for your attention. Very